You will not believe what 3I Atlas has just caused. It is not a catastrophe nor a global danger alert, but what this interstellar object provoked was enough to ignite debates among scientists, astronomers, and even political figures in different countries. What seemed to be just another celestial body crossing the solar system is now generating a level of attention that no specialist expected so soon. It all began with new data observed by international telescopes, showing unexpected changes in its brightness and in the way it reflects sunlight, which led several experts to question whether we truly understand the behavior of objects coming from outside our system. The reactions were swift. Some scientists demanded more instruments be pointed at 3I Atlas, while others said it is nothing out of the ordinary and that we are merely seeing ice sublimate as it approaches the sun. However, what caused the most controversy was that official bodies began discussing whether these objects should be included in planetary defense protocols, not because they represent a threat, but because their origin and trajectory could help develop new early detection strategies. And it is precisely there that everything left the scientific world and reached public conversations, media outlets, and political discussions. Why is an object that is not even coming close to Earth generating so many decisions, documents, and private meetings among space agencies? What exactly did the telescopes observe to trigger all of this? Before explaining what is happening with 3I Atlas, it is important to understand why this object is attracting so much attention. Thousands of bodies travel through space every year, but very few come from outside the solar system. 3I Atlas is one of them. It was detected by the Atlas observation system, and since then astronomers from all over the world have followed its every movement. Its trajectory is not like that of a common comet, and its physical characteristics also do not behave as expected. It does not represent a danger to Earth, but it is changing the way scientists and governments think about interstellar objects. Before we dive into the sudden brightness surge of the interstellar comet 3I/Atlas during its perihelion and its possible coincidence with the strongest solar activity in decades, you need to do 3 things right now to activate the global scientific community. First, hit like on this video to boost this interstellar discovery to more sky watchers. Second, subscribe and turn on the bell to get the next real-time updates on its hyperbolic trajectory tracking. And third, scroll down to the comments right now and write 3I Atlas to join the global registry of those following this visitor from another star. Do it now. Returning to the topic, the most surprising thing is not just what the telescopes recorded, but everything that was generated afterward. Meetings between space agencies, requests for additional time at observatories, and discussions about whether the protocols for detecting interstellar visitors should be updated. All of this without any announced danger, which leaves an open question. If there is no risk, why so much reaction? 3I Atlas is not a common comet nor a simple piece of rock wandering through space. Its designation 3I means it is the third interstellar object ever detected crossing our solar system, after Oumuamua and Borisov in 2019. It was discovered by the Atlas system, a set of telescopes in Hawaii designed to detect bodies that could represent a threat to Earth. However, what they found was not dangerous but intriguing. A visitor coming from beyond the sun's gravity, possibly from another star, traveling through space for millions of years before being seen from our planet. From the moment of its detection, astronomers calculated its trajectory and confirmed something surprising. The orbit of 3I Atlas is not closed like that of planets or common comets, but hyperbolic, which means it is not bound to the sun by gravity and will continue on its path into interstellar space after its passage. This type of trajectory leaves no doubt about its external origin. To calculate it, scientists relied on repeated observations, recording its exact position in the sky. With this data, they measured the orbital eccentricity, a number that indicates how open or closed the trajectory is. For objects bound to the sun, this value is less than 1. For 3I Atlas, it exceeds that value, confirming its interstellar nature. But what caused more reaction was not simply its origin, but a change in its behavior. Its brightness began to vary unexpectedly. When an icy object like this approaches the sun, the heat causes the ice to sublimate, that is, it passes directly from solid to gas, and that forms a coma and, in some cases, a tail. That is normal. The unexpected part was that the increase in brightness did not coincide with the expected distance to the sun. It seemed to become more active earlier than calculated and with an intensity greater than common for an object of its size. Several observatories began recording these variations. Within days, internal reports appeared among scientific institutions suggesting that perhaps something in the composition of 3I Atlas was different from what had been seen before, possibly a mixture of carbon dioxide ice, carbon monoxide, and other volatile compounds that sublimate at lower temperatures, which would explain why it was glowing earlier than expected. This type of behavior is not dangerous, but it is very valuable scientifically, because it provides clues about how objects form in other stellar systems. As data was published, discussions also began to emerge outside of astronomy. NASA's Planetary Defense Coordination Office, responsible for monitoring near-Earth objects, requested more information about the trajectory of 3I Atlas, not because it represented a risk, but because understanding it would help improve early warning systems for future interstellar visitors that could be dangerous. Other agencies joined the interest. There was even talk of possible future missions to intercept similar objects as part of exploration or defense programs. The surprising thing was that the conversation left scientific forums and reached political instances. Some officials requested detailed reports, not out of fear, but because an interstellar object observed so closely is a unique opportunity to gather data. They discussed whether more investment should be made in terrestrial and space telescopes capable of detecting these bodies with greater anticipation. What 3I Atlas caused was not panic, but a shift in priorities and accelerated conversations about how the planet should react to interstellar visitors. Another key point was when several astronomers requested observation time on the James Webb Space Telescope, the most advanced to date. With its infrared precision, the JWST can analyze the reflected light and determine the object's chemical composition. This is vital because studying a fragment from another stellar system could reveal how planets formed in places completely different from our own. There is still no public confirmation if the James Webb has already directly observed 3I Atlas, but it is known that there are formal requests to do so. Despite all this interest, something must be made completely clear. 3I Atlas does not represent a threat to Earth. Its trajectory does not approach our planet in a dangerous way, nor is there any possibility of impact. The distances are enormous. So why does it continue to generate so much movement? Because every interstellar object is like a message from deep space, a piece of another solar system that reaches us, and that does not happen every year. It is rare, valuable, and scientifically irreplaceable. Another reason the topic grew was because exaggerated interpretations began circulating on social media and in communication outlets. Some headlines mentioned danger, mystery, or theories without scientific basis, which forced institutions to publish clarifications. Scientists have been firm. There is no risk, no artificial signals, no evidence that it is anything more than a natural object of interstellar origin. What there is an extraordinary opportunity to do science and improve the way the planet detects and studies phenomena from space. Thanks to this panorama, 3I Atlas went from being an almost unknown object to becoming a central topic in astronomical conferences and technical documents. Its arrival has generated new proposals for rapid exploration missions, ideas about interceptor probes, and deeper analysis of materials that formed far from our Sun. This is what it has truly caused. Although 3I Atlas is not yet visible to the naked eye, the observatories tracking it closely have detected changes in its brightness that do not match what was expected for an object of its size and distance. This anomalous behavior implies no danger, but it has tested the current models about the activity of interstellar bodies. Normally, when an object of this type approaches the Sun, the most volatile ices begin to sublimate and generate an envelope of luminous gas and dust. However, in this case, the brightness increases happened faster, as if certain compounds were activating sooner than anticipated. This led many scientists to think that its composition could be very different from that of traditional comets in the solar system. Preliminary studies indicate it could contain large amounts of frozen carbon monoxide and carbon dioxide, substances that sublimate at lower temperatures than water ice. If that is true, it would explain why it began emitting dust and gas from a greater distance than usual. Telescopes have confirmed slight variations in the coma of 3I Atlas, which confirms that its activity is already present. Some astronomers suggest it could be one of the most active interstellar objects observed to date, not because of its size, but because of its chemical composition. Besides the scientific data, what made 3I Atlas more relevant was that after these observations, several institutions began updating mathematical models to predict its trajectory with greater precision. Although it was already known that it would not represent any impact risk, some research groups pointed out that this object is ideal for testing early warning systems and defensive simulations. This is not alarmism, but about using every opportunity to improve global detection and analysis protocols. Another interesting point is that 3I Atlas does not move in a completely uniform way. Small variations in its direction have been recorded, probably due to the activity of gases being released from its surface. This effect is known as non-gravitational acceleration and had already been observed in Oumuamua. It is as if the gas jets act like small natural thrusters that minimally alter its path. For orbital studies, these details are fundamental because they allow for more precise calculation of what types of materials it contains and how they interact with sunlight. While optical telescopes observed its brightness changes, other instruments began analyzing the reflected light to determine which molecules are present. The information is still partial, but the data points to a mixture of dust, ice, and complex organic compounds, similar to those found in solar system comets, but with different proportions. This reinforces the idea that in other stellar systems, icy bodies form differently under other chemical conditions and temperatures. Every observation of 3I Atlas is actually a window into the history of another place in the universe. What generated surprise was not only its physical behavior, but the reaction in scientific and technological circles. Several research centers proposed increasing the network of automated telescopes to track objects approaching from outside the ecliptic plane, since many of them, like this one, do not follow common trajectories. NASA and ESA began considering if future missions could be adjusted in time or designed to intercept objects of this type. Although intercepting 3I Atlas is impossible due to its speed and trajectory, its passage is boosting the planning of missions for future interstellar visitors. An important topic also emerged: reaction time. 3I Atlas was detected with reasonable anticipation, but still many astronomers believe we need more sensitive instruments located in different points of the planet to have even earlier alerts. This would allow for coordinated observation planning, allocation of time on space telescopes, and more in-depth analysis of these uncommon bodies. Every day of anticipation counts to obtain more scientific data before the object moves away definitively. Meanwhile, media outlets and social networks began amplifying the topic, sometimes with exaggerations. Therefore, official institutions were forced to issue statements clarifying that there is no threat, that there is no evidence of anything beyond the natural, and that the interest arises from what can be learned scientifically. Experts in space outreach explained that the important thing is not the risk, but the opportunity, to understand how other planetary systems form, what materials exist outside our own, and what the space between stars is like. At this point, 3I Atlas became a symbol of something much larger. It reminded us how little we know about interstellar space and how much we have yet to discover. It is a natural message traveling from unknown regions, bringing fragments of ice, rock, and compounds we have never had so close before. Its passage is not a danger, it is a lesson. And that is why it has provoked scientific meetings, technical analyses, debates about investment in telescopes, and discussions about whether we should be prepared for when a similar, but larger or less safe, object arrives. Adding to all this is a fundamental element: time. The perihelion, the point at which it will be closest to the Sun, will occur in 2025. As it approaches, its activity will increase, it will release more gases and dust, and its brightness could grow enough to be visible with binoculars or even to the naked eye from dark locations. That will be the best opportunity to study it. Afterwards, it will move away forever, returning to the interstellar void. If we do not analyze it now, there will be no second chance. That is why so many scientists are acting now and not later. With all this, it is clear that what 3I Atlas has caused is not a destructive physical event, but an intellectual and technological reaction. It has prompted questions, research, adjustments in protocols, and a race to obtain the maximum amount of data before it disappears. It does not bring danger, it brings knowledge, and that could be even more valuable. The scientific importance of 3I Atlas lies not only in its rarity as an interstellar traveler, but also in what it can reveal about the functioning of the solar system in the face of objects that did not form here. To better understand why it has generated so much interest among astronomers and planetary scientists, it is necessary to analyze how it interacts with the solar environment. Every object that approaches the Sun is affected by radiation, the solar wind, and gravity. But in the case of interstellar bodies like this one, the way they respond can be different due to their composition and their previous thermal history, having spent millions of years in extremely cold regions far from any star. One of the most studied aspects has been the way sunlight heats its surface. In solar system comets, water ice begins to sublimate at a specific distance from the Sun, releasing gas and dust. However, with 3I Atlas, activity was observed at a distance where common comets normally remain inactive. This behavior suggests the presence of substances much more volatile than water, such as frozen carbon monoxide or carbon dioxide, which can sublimate at lower temperatures. This detail indicates that its place of origin could have been an outer region of another planetary system, perhaps similar to the Oort cloud, but around another star. Astronomers have used spectroscopy to study the light reflected by the object and break it down into wavelengths, which allows for the identification of which molecules are present in its coma. Although the results are still being analyzed, weak signals of complex organic compounds have been reported, reinforcing the idea that the basic ingredients for life can be distributed throughout the galaxy in icy bodies like this. It does not mean there is life nor that it is an indication of it, but that the essential chemical elements can travel through space in this type of object. Even though the activity of 3I Atlas has been subtle compared to very active comets within the solar system, any observed change is extremely valuable because initiating activity at great distances from the Sun is infrequent. Some scientists compare what is happening now with what was observed in 2I/Borisov, the second detected interstellar object, which did present a clearly visible coma and tail, but even between the two there are differences. Borisov had behavior more similar to a classic comet, while 3I Atlas demonstrates less intense but earlier variations. Another key point has been the exact trajectory of 3I Atlas. Its orbit is hyperbolic, which confirms that it is not bound to the Sun and that once it crosses the perihelion it will continue on its path to the exterior of the solar system and return to interstellar space. This trajectory has been calculated using repeated and precise observations of its apparent position in the sky. With this data, a mathematical adjustment called the least squares method is applied, which allows for the determination of the orbital eccentricity. In this case, that value is greater than 1, which indicates that its orbit is not a closed ellipse, but an open curve. The speed at which it travels has also been of interest. Upon entering the solar system, it is estimated that 3I Atlas had an interstellar velocity of approximately 26 to 30 kilometers per second. As it approaches the Sun, solar gravity increases that speed, as occurs with any object attracted by a star. When passing through the perihelion, it will reach its maximum speed, and subsequently, gravity will slow it down slightly as it moves away, although never enough to stop it. It will finally escape with a residual velocity that will allow it to continue its journey into the void, where it will never be observed again. The analysis of its surface has also generated interesting hypotheses. Although detailed images are not yet available, the brightness variations indicate that it is not completely uniform. This could be because some regions of its surface contain materials that sublimate faster than others, creating active and inactive zones. This non-uniform distribution can provoke small forces that slightly alter its trajectory, something similar to what was seen with Oumuamua. To detect these variations, changes in its apparent magnitude are measured and compared to models of rotation and light reflection. Meanwhile, radio observatories are trying to capture signals that could indicate the presence of specific molecules like hydrogen cyanide, ammonia, or other compounds present in comets. No artificial signals or anything suggesting technology have been detected, and scientists have been very clear in communicating this to avoid misunderstandings. Everything observed so far points to a natural object, but one with characteristics that could provide invaluable information about the origin and evolution of matter outside our system. This scientific interest has also reactivated conversations about the possibility of future missions that could travel quickly to intercept this type of object. Although it is impossible to reach it now because it moves too fast and there was no time to prepare a mission, agencies are already developing projects like Comet Interceptor, a spacecraft designed to wait in space and head towards unstudied comets or even interstellar visitors. The passage of 3I Atlas has reinforced the need for that type of technology. The perihelion, which will occur in 2025, will be the closest point to the Sun in its journey. After that, the object will visually fade as it moves away and will lose activity. For this reason, the period between 2024 and 2025 is critical for recording data. Scientists are trying to secure observation time on major telescopes during those dates, as it would be the last opportunity to obtain direct information about its coma and composition before it becomes too faint to be measured with precision. What is happening with 3I Atlas is not a dramatic or dangerous event, but an opportunity for knowledge. But that opportunity will not repeat itself. When it moves away and returns to interstellar space, there will be no way to reach it or study it again. That is why it generates so much attention, so many debates, and so many scientific and technical decisions. It is a race against time, not to save the planet but to learn about it and about the worlds that exist beyond our reach. One of the most interesting aspects of 3I Atlas is the way its presence has forced different research centers to coordinate as rarely happens. It is not just about individual observatories pointing their telescopes at the same point in the sky. It is a global network of scientists, universities, and space agencies sharing data almost in real time, comparing measurements and refining models. Every observation, every change in its brightness, every slight variation in its trajectory is incorporated into databases that are analyzed by specialists in orbital dynamics, space chemistry, and planetary formation. This coordination shows that although the object does not represent a danger, it is considered scientifically a priority. This type of collaboration is not common for all comets. What makes 3I Atlas different is its origin and the fact that, by coming from another stellar system, it offers a natural sample of materials that did not form under the same conditions as the planets, asteroids, and comets of the solar system. To better understand its importance, it is enough to remember that Oumuamua could only be studied for a few weeks before becoming too faint for the most powerful telescopes. With 2I/Borisov, more information was obtained, but it was still insufficient to know its internal composition with precision. Now, with 3I Atlas, scientists do not want to repeat that story and are acting before it is too late. Another relevant element is how the analysis of 3I Atlas helps evaluate whether the models we use to describe interstellar comets are correct or need adjustment. Every time its brightness is measured, its production of dust and gas is calculated, which allows for estimating the proportion of volatile materials on its surface. If these values do not match what is expected, researchers must modify the thermodynamic models that predict the sublimation of different compounds. This is essential not only for understanding this object but also for anticipating how others that arrive in the future might behave. So far, one of the most interesting results is that the activity of 3I Atlas began at distances greater than what occurs in the majority of solar system comets. This supports the idea that its surface contains large amounts of frozen carbon monoxide and carbon dioxide, which sublimate at lower temperatures. However, the presence of other more exotic compounds or chemical combinations that have not been seen so clearly in local comets cannot yet be ruled out. For this reason, telescopes like the James Webb represent a key tool, as they can analyze the infrared spectrum with a level of precision that terrestrial instruments cannot match. Despite this, obtaining observation time on the James Webb is not so simple. Every minute of use must be requested months in advance, accompanied by a detailed scientific proposal justifying its importance. In the case of 3I Atlas, several requests have been sent by teams from different countries. Some have been accepted, others are under evaluation, and some were rejected due to time and scheduling limitations. But the mere fact that so many groups are competing to study the same object demonstrates the scientific impact its arrival has generated. In parallel, telescopes continue observing the coma and dust tails of active comets, which allows for direct comparison of their characteristics with those of 3I Atlas. Although the Hubble Space Telescope does not have the same infrared sensitivity as the James Webb, it remains valuable for its ability to capture high-resolution images in the visible spectrum. If 3I Atlas develops a sufficiently bright coma during its perihelion in 2025, it is likely that its observation with this telescope will be prioritized to obtain detailed images before it disappears from our reach. Another aspect that has awakened scientific interest is that this object not only shows us how bodies native to another system behave, but also how our own solar system reacts to its presence. Solar radiation, the solar wind, the heliospheric magnetic field, and the gravity of the planets affect an interstellar object differently compared to those that have been under their influence for thousands of years. This type of interaction can be measured indirectly through the way the object's coma expands or distorts, which also allows for the study of the properties of the interplanetary medium. Furthermore, studying this interstellar visitor helps answer a question that has been open for decades. How often do objects like this cross our solar system? Before the discovery of Oumuamua, many scientists believed these events were extremely rare, perhaps one every millions of years. But then came Borisov and now Atlas in less than a decade, suggesting they could be more common than thought. This means that improving detection systems is not only useful for planetary defense, but also for science because we could study multiple interstellar objects during this century if we have the correct technology. In this context, discussions about investment in new telescopes have gained strength. Projects like the Vera C. Rubin Observatory in Chile, which will begin operations soon, are designed to scan the entire sky every few nights and detect any moving object, even if it is faint or traveling in an unusual direction. This type of facility will be crucial for detecting future interstellar visitors with more anticipation and observing them under better conditions. All of this shows that what 3I Atlas caused was not a dramatic physical event, but a profound effect on science, technology, and international coordination. It generated questions, accelerated research, and reinforced the idea that we live in a dynamic universe, where even the smallest objects can have an enormous impact on our knowledge. It did not provoke destruction but curiosity, and that is perhaps the most powerful consequence. The interest in 3I Atlas comes not only from astronomers observing its trajectory, but also from specialists in orbital dynamics, physicists of cosmic dust, and scientists who study how planetary systems form. Each one sees in this object an opportunity to resolve questions that until now could only be answered with theories or simulations. One of those questions is, how do comets and icy bodies form in other solar systems? And how do they manage to escape the gravity of their parent star? It is thought that these objects are expelled during the early stages of planetary formation, when giant planets gravitationally alter smaller bodies and launch them into interstellar space. When one of these objects travels for millions of years to our solar system, it brings with it clues about the place where it formed. The composition of its ice, the proportions of trapped gases, and the presence of organic compounds are like a chemical record of its origin. Comets in the solar system have already been studied in great detail, especially after missions like Rosetta, which orbited Comet 67P Churyumov-Gerasimenko. But we have never been able to directly study a comet formed in another stellar system. That is why, although 3I Atlas cannot be visited by a spacecraft, every light spectrum and every recorded brightness curve provides unique data. It has also generated interest among planetary defense experts, although not because it represents a threat. The important thing is that this object forces the testing of systems that would be used if one day an interstellar body appeared on an impact trajectory. The algorithms that calculate hyperbolic orbits, the tracking networks, and the communication protocols between space agencies are being used for practice and improvement. Thus, when a truly dangerous object arises, the scientific community and warning systems will be more prepared. In this way, 3I Atlas does not cause fear, but it does motivate preparation and coordination. The object's behavior has also become a tool for studying the interaction between solar radiation and interstellar bodies. The solar wind, composed of particles emitted by the sun, collides with the gases and dust released from the object. This forms structures like ionized gas tails or dust tails that extend in the direction opposite the sun. Although in the case of 3I Atlas, these structures are not yet visible to the naked eye nor clearly distinguishable in small telescopes, the most advanced instruments are already recording signs of a slight coma. As it gets closer to the sun, these structures could become more evident. The study of those tails and the shape of the coma allows for the determination of the pressure exerted by solar radiation on the object. This analysis also helps to know the size of its dust particles. By measuring how the light scatters, one can estimate if the dust is fine like smoke or if it contains coarser grains. In solar system comets, these particles vary depending on the composition and the time the comet has spent near the sun. In the case of 3I Atlas, since this is its first approach to any star in a long time, it is likely that its dust preserves very primitive conditions, almost intact since its formation. Despite this, some scientists have warned that not everything can be known with certainty through remote observations alone. To deeply understand this type of object, it would be ideal to send a mission that could approach, take samples, or even land. However, the speed and trajectory of 3I Atlas make it impossible to reach with current technology. That is why missions are being designed to be already in space and able to quickly head towards a new object as soon as it is detected. This requires having spacecraft ready at strategic points, from where they can be launched in a short time towards diverse trajectories. Some projects are already in development with this idea. One of the most advanced is the European Space Agency's Comet Interceptor, which will be launched to wait in space until an unstudied comet or an interstellar visitor appears. When that happens, it will head towards it and study it up close. The arrival of 3I Atlas has reinforced the arguments for this type of mission because it demonstrates that interstellar objects are not rare and that it is possible to take advantage of them to obtain scientific data never before available. Another important element is the role of the general public. Although many people become interested in these topics thanks to the media or social networks, erroneous or exaggerated interpretations can also appear. That is why scientific institutions have been careful to communicate that 3I Atlas does not represent a risk to Earth. It is not heading towards us, it will not change its trajectory towards our planet, and there is no evidence of physical effects caused by its passage. The only thing it has caused are scientific debates, adjustments in mathematical models, and decisions about observation and exploration. Clarity in this communication is important because it prevents panic and keeps the focus on what truly has value: knowledge. By better understanding how these objects behave, we can learn about the formation of planetary systems, about how materials are distributed in the galaxy, and about the possible origins of organic molecules in different places in the universe. All of this contributes to building a more complete picture of our place in the cosmos based on verifiable data and not on assumptions. The passage of 3I Atlas has also raised a fundamental question. How much do we really know about interstellar space? Between the stars there is not simply a vacuum. There is gas, dust, magnetic fields, and radiation. However, these regions are extremely difficult to study directly. Interstellar objects like 3I Atlas act as natural probes that travel through those zones and reach us with information embedded in their composition. Every time one crosses our system, we have a unique opportunity to observe material that has traveled farther than any spacecraft sent by humanity. When 3I Atlas completes its passage around the Sun and moves away, it will be practically impossible to observe it in detail again. The object's light will weaken, its coma will disappear, and it will slowly be lost among the background stars. For that reason, time is essential. Every night of observation counts. Every recorded spectrum is valuable. Every calculation about its orbit and composition helps to build a clearer picture, not only of this object but of how the universe functions. The passage of 3I Atlas is also generating an important change in the way we understand the relationship between our system and outer space. Traditionally, it was thought that planetary systems were isolated structures, formed and evolving independently. However, the fact that objects exist capable of escaping from one star and traveling for millions of years to reach another demonstrates that systems are not completely separate. There is a natural exchange of matter on a galactic scale. This means that fragments from other systems can cross ours, and at the same time materials from the solar system could be traveling far away towards distant stars. 3I Atlas is tangible proof of that cosmic exchange. Another issue that has sparked interest is how these objects can be a key source for studying the chemistry of deep space. The composition of 3I Atlas may contain molecules formed in extremely cold environments, far from the radiation of a star. These molecules, trapped in the ice for millions of years, could reveal what the chemical environment where it originated was like. Some telescopes have already detected signals of simple organic compounds, which is not evidence of life, but does demonstrate that the basic ingredients for it to arise are present in various corners of the universe. Every analysis of 3I Atlas is a small piece of that puzzle. While this is happening, astronomers continue to measure its movement with precision. The hyperbolic orbit it follows allows for the calculation of its speed, its past trajectory, and its future path. To achieve this, observations from different points on Earth and at different times of the night are used. Afterwards, through complex numerical calculations, the object's position in space is determined exactly and its trajectory beyond the perihelion is projected. The results show that it does not approach Earth or any large planet dangerously, although it will pass relatively close to Mars at a safe distance. That passage will not cause any effect on the red planet, but it could facilitate observations from orbiters already there, like those from NASA and ESA. The study of this object also helps to better understand the influence of the solar wind. As it approaches the Sun, the charged particles expelled by our star collide against the coma surrounding the object, generating a possible ion tail. This allows for the indirect measurement of certain properties of the solar wind and the heliosphere. The heliosphere is a kind of bubble created by the Sun, within which our entire system is located. Beyond this bubble begins the interstellar medium. 3I Atlas comes precisely from that exterior and is now interacting with conditions new to its history. This transition is unique because it offers information about how an interstellar object responds to the solar environment for the first time in millions of years. Another important element is temperature. In the distant regions of interstellar space, temperatures can fall below 260 degrees Celsius. Upon entering the solar system, the object heats up slowly. This causes the ices to begin sublimating depending on their freezing point. The process releases trapped gases and forms the coma. The speed at which this happens depends on its rotation, whether it has cracks, the orientation of the Sun, and its chemical composition. Scientists are trying to determine its rotation period by measuring variations in its brightness. If an object spins, small, more reflective or active zones can cause changes in the light it emits. These patterns allow us to know how long it takes to complete one rotation around itself. So far, the data obtained indicate it could have a relatively slow rotation, although there is no consensus yet. This is important because if the object spins slowly, it can sublimate unevenly, provoking small variations in its trajectory due to gas escape. This phenomenon was observed in Oumuamua, which complicated its orbit. In the case of 3I Atlas, understanding its rotation will help to further improve the mathematical models that predict its path. The more precise the model, the easier it will be to study future similar objects. The cultural impact of this object is also notable. Although it does not represent danger, it has captured the attention of millions of people. This is not because it brings destruction but because it represents something more profound. The confirmation that we are not isolated, that fragments from other systems can visit us naturally, that there is much we do not know, and that despite all the telescopes, satellites, and probes, we continue to be witnesses to phenomena that surprise us. This reality has led many people to become interested in astronomy, to follow observatories, to ask what 3I Atlas is and why so many scientists are talking about it. It has also opened debates about the possibility of finding more interstellar objects if we have better instruments. Before, these bodies were impossible to detect because they entered and left the system unseen. Now, with automated systems and high-sensitivity cameras, we can detect them with enough time to study them. The question is not if another will appear, but when it will, and if we will be prepared to observe it clearly from the beginning, capture its light, analyze its chemistry, and perhaps in the future send a probe to reach it. At this moment, telescopes all over the world continue to collect data. Some work in the visible spectrum, others in infrared, radio, or ultraviolet. Every observation adds to an archive that grows day by day and that will later be analyzed for years, even when the object has already disappeared from the skies. Perhaps within a few decades, what we learn from 3I Atlas will be used to understand how planets formed around distant stars or how essential molecules for life can travel from one system to another. Although 3I Atlas does not represent a threat to Earth, its arrival has provoked a profound change in the way we think about interstellar objects, not only from a scientific point of view, but also technological and philosophical. This object has been traveling through space for millions of years, very possibly expelled from another planetary system when it was still in formation. During all that time it remained in darkness, frozen, without approaching any star, until it finally entered the sun's gravitational field. That makes it a time capsule, an intact fragment of the past of another solar system preserved at extremely low temperatures until now. One of the reasons scientists are focused on studying it is that, unlike comets in our solar system, 3I Atlas had never before been heated by a star. It has not been modified by sublimation cycles, nor has it lost gas or material in previous orbits. What we observe today is probably its first interaction with solar radiation, which makes it an exceptional laboratory for studying the original components of a stellar system foreign to our own. Every molecule it releases, every change in its brightness, and every fragment of expelled dust is pure information about its origin. But what has truly generated mobilization in the scientific community is not only its rarity, but the limited opportunity to study it. Unlike planets or comets in the solar system, which we can observe repeatedly, 3I Atlas will enter and exit only once. It will not return, it will not remain in orbit. It will pass near the Sun, reach its closest point during the perihelion in 2025, and then continue its journey towards the exterior, becoming increasingly faint until it disappears from our telescopes. That certainty generates urgency because every observation, however minimal, is valuable forever. One of the most discussed questions among astronomers is, how exactly do these objects originate? It is believed they come from the most distant regions of other planetary systems, similar to what in ours would be the Oort cloud. When a giant planet like Jupiter forms, its enormous gravity can destabilize the orbits of thousands of icy bodies, expelling many of them into interstellar space. Some become trapped around the star, others escape completely. It is likely that 3I Atlas is one of those expelled. The fascinating thing is that by being expelled during the planetary formation process, its composition may contain information about how rocky, gaseous, and icy planets formed in that system of origin. Another factor that generates scientific interest is that this object allows for the study of how interstellar materials behave when they enter into contact for the first time with the solar system's environment. Upon crossing the heliosphere, the region influenced by the solar wind and the sun's magnetic field, high-energy particles, radiation, and magnetic fields affect its surface. The way its ice responds to this exposure can reveal details about the surface composition, the distribution of dust, and the presence of organic compounds. Although we cannot physically touch it, measuring its light spectrum allows us to obtain information about these processes with great precision. The observations are also being used to improve computational models about hyperbolic trajectories. Although 3I Atlas does not represent danger, what is learned today will serve to better calculate the movement of future objects that could approach closer to Earth. Knowing how small forces like solar radiation pressure or gas expulsion affect its orbit allows for the adjustment of early warning systems. This knowledge could in the future save lives if an interstellar object arrived on an impact trajectory. At the same time, the study of 3I Atlas has reignited a deeper scientific discussion. How many objects like this cross our solar system each year? For centuries it was thought they were extremely rare, but in less than a decade, 3 have already been detected: Oumuamua, Borisov, and Atlas. This suggests that perhaps they have always been passing through, but we did not have the technology to detect them. Today, thanks to automated telescopes, wide-field cameras, and tracking algorithms, we are capable of seeing that which was previously invisible. This completely changes our view of how connected we are to the rest of the galaxy. It is also important to clarify that 3I Atlas has not caused any physical changes on Earth, nor atmospheric alterations, nor gravitational perturbations. What it has caused is something less dramatic, but much more profound. Scientific reorganization, debates, observation requests, academic meetings, and decisions about technological investment. No official body has issued risk alerts. No space agency has declared danger. What they have communicated is that it is a historic opportunity to learn. The media and social networks have amplified the news, sometimes responsibly and other times not so much. Therefore, professional observatories have had to publish notes clarifying what 3I Atlas is, where it comes from, what has been observed, and what has not. It is insisted that it is not an artificial object, it does not emit technological signals, it does not change its trajectory towards Earth, and there is no evidence that it causes effects on our planet. Everything that is happening revolves around knowledge, not danger. Every night that passes, telescopes in Chile, Hawaii, Spain, Mexico, Australia, the United States, and other places point their lenses at the same point in the sky to follow the object. Every piece of data collected will be studied for years. Even when the object disappears, the information will remain stored, analyzed, and compared with models of stellar system formation. What we learn from it may help to understand how our own system formed 4.6 billion years ago, when there were also comets, ice, rocks, and dust floating before becoming planets. And perhaps when 3I Atlas moves away and its brightness is lost, the most valuable thing will not be what we saw, but what we understood: that the universe is alive, that planetary systems are not isolated worlds, and that small fragments from other suns can travel to us, touch our telescopes, and then return to the silence of space forever. The scientific community has made it clear that the most valuable aspect of 3I Atlas is not its physical presence, but what it represents for human knowledge. It is not an object that will alter life on Earth, nor a phenomenon that provokes gravitational or atmospheric effects. The truly important thing is that this interstellar visitor allows us to observe for the first time materials that formed outside our solar system and that have remained intact for millions of years in deep space. Every fragment of dust, every molecule released as it approaches the sun is direct evidence of chemical and physical conditions that do not exist in our immediate environment. What 3I Atlas has caused is not fear but questions. It has provoked universities, space agencies, and research centers to momentarily halt their priorities to look at the sky with more attention. It has forced a rethinking of how we detect objects on hyperbolic trajectories, how we study them before they disappear, and how we might intercept them if one day it were deemed necessary. Although its passage is not dangerous, it is helping to reinforce global observation protocols and alert systems, not for what may happen now, but to be better prepared for the future. One of the most active areas of research is spectroscopy, which is the analysis of light emitted or reflected by the object. Sunlight bounces off its surface and the gases of its coma, and when broken down, characteristic signatures of different chemical compounds can be identified. This process allows for the distinction of the presence of carbon monoxide, frozen carbon dioxide, water, methane, and organic molecules. Preliminary data indicate that 3I Atlas has a mixture of ice similar to that of solar system comets, but with different proportions, which suggests a different formation environment. These results not only confirm its interstellar origin but also offer clues about the chemistry of other planetary systems. The analysis of its trajectory continues to confirm that it is not under the Sun's gravitational influence. Its orbital eccentricity is greater than 1, which defines a hyperbolic orbit. This means it will reach its maximum speed at perihelion, and then escape again into space. Before its discovery, it was thought that interstellar objects could be extremely rare, but now it is clear that they can cross our system more frequently than imagined. The difference is that now we have the technology to detect them, measure them, and study them systematically. The fact that 3I Atlas was detected with so much anticipation has given enough time to organize global observation campaigns. Small and large telescopes located on different continents have been measuring its brightness, its coma, and its apparent position in the sky. These measurements allow for the refinement of its orbit and the obtaining of more precise data. Some observatories are also using special filters to isolate certain wavelengths of light and with them detect the presence of ionized gas, which would indicate interaction with the solar wind. Another relevant aspect is that this object is providing new information about how interstellar bodies interact with the heliosphere, which is the region dominated by the magnetic field and solar wind emitted by our star. When the object approaches, it traverses this zone and for the first time suffers the effects of the solar wind. The shape of its coma and the possible formation of an ion gas tail could reveal details about the pressure of the solar wind, the intensity of the magnetic field, and the conditions of interplanetary space. Solar radiation pressure also influences its behavior. Sunlight exerts a constant force on the dust released from the object, pushing it in the direction opposite the star. These small pushes, although they seem insignificant, can cause detectable changes in the trajectory of 3I Atlas. Analyzing these changes allows for the estimation of the size and density of the dust particles. In the case of this object, the data suggest it is releasing very small particles, probably due to the early sublimation of very volatile compounds. Several research teams are also studying the light curve of 3I Atlas, which is a graph showing how its brightness changes over time. If the object has a defined rotation, that movement can produce periodic variations in the amount of reflected light. This allows for the estimation of its rotation period, its shape, and whether it has more active zones than others. Although the data are still not conclusive, some analyses suggest it could have a slow rotation compared to other comets. This behavior could be due to its internal structure, its density, or its formation history. Experts have insisted that 3I Atlas will not provoke physical changes on Earth. It does not represent a threat, it will not emit dangerous radiation, it will not affect the planet's gravity, and it will not alter the climate. The reason it has generated so much attention is because its study can change how we understand the formation of stellar systems and the distribution of matter in the galaxy. Every piece of data collected is valuable not because it protects us from something but because it helps us better comprehend our place in the universe. When it gets closer to the Sun, during its perihelion in 2025, scientists expect its activity to increase and for it to release more gas and dust. That will be the best time to observe it. If its brightness increases enough, it will be visible even with binoculars from dark locations. Then, as it moves away from the Sun, it will lose activity. Its coma will fade and disappear into the background of the sky. It will not return, it will not orbit the Sun again. It will continue its path towards more distant regions, where not even our most powerful telescopes will be able to follow it. Therefore, what it has caused should not be measured in terms of physical effects, but in terms of knowledge. It has propelled research, international coordination, technological development, and scientific debate. It has reminded the world that the universe is full of objects traveling from one system to another, invisible, until the sunlight illuminates them, and that even though we cannot reach them, we can learn from them as much as our tools allow. The interest awakened by 3I Atlas has also driven the creation of new observation strategies, not only for this particular object, but for all that may arrive in the future. One of the biggest challenges for astronomers is that interstellar objects travel at very high speeds and are only detectable for a short period of time. In the case of 3I Atlas, it was identified with sufficient anticipation to analyze it before its perihelion, but that is not always the case. Therefore, different observatories around the world are integrating automated systems that review images of the sky every night in search of objects that do not match known trajectories. These systems use artificial intelligence to recognize patterns, calculate orbits, and alert researchers almost in real time. Although 3I Atlas does not represent a danger, its study serves as a practical simulation for the scientific community to test its tools. This includes networks of observatories, computational programs for orbital prediction, and communication protocols between space agencies. NASA's Planetary Defense Coordination Office, although it does not consider it a threat, has used its passage to evaluate how quickly verified information can be shared, how updates are disseminated to the public, and how efficient cooperation between countries is when dealing with an object originating outside the solar system. This is not alarmism, but preparation based on science. The behavior of 3I Atlas has also contributed to improving our understanding of how objects react to solar heating. As it has been approaching the Sun, its nucleus has begun to release gases that were trapped in the ice since its formation. This release creates a coma, a kind of cloud that envelopes the nucleus, and potentially a tail that extends in the direction opposite the Sun. In this object, the complete activity is still faint, but sufficient for sensitive instruments to detect changes in its apparent magnitude. Some studies have recorded small bursts of brightness known as cometary outbursts, which could be due to cracks on the surface or the sudden release of accumulated gas. These phenomena allow for the study of the object's internal structure. If the outbursts are frequent and strong, it can indicate a fragile surface composed of thin layers of dust covering ice. If they are scarce, it can suggest a more compact crust. In the case of 3I Atlas, the reported outbursts have been moderate, which suggests that its surface may have a relatively uniform mixture of dust and ice. By analyzing the speed at which the released dust expands, researchers can also calculate the density of the material and the temperature of the nucleus. Another topic of interest is the gravitational effect of the solar system's planets on its trajectory. Although 3I Atlas does not come close enough to any planet to be drastically deflected, the small gravitational interactions with Jupiter and Saturn are measured with precision. These measurements help to improve the orbital simulation models that predict how interstellar objects behave within the Sun's influence. In this case, it has been confirmed that no gravitational force will change its course towards Earth. After the perihelion, it will continue moving away until it completely exits the heliosphere and returns to the interstellar medium, probably never to return. The scientific analysis of 3I Atlas has also spurred comparative studies with Oumuamua and Borisov. The first did not show a defined coma, which caused confusion about whether it was a comet, an asteroid, or something in between. The second did have a clear coma, but its behavior was similar to a typical solar system comet. 3I Atlas finds itself between both cases. It has activity but not as intense as Borisov, and its brightness varies more regularly than Oumuamua's. This combination suggests that interstellar objects can be as diverse as the bodies that exist within our system. This opens an important question. How many different types could we find if we had better instruments? Thanks to this object, scientists have also begun to consider whether spectrometers from Earth's orbit or even from lunar bases could be used in the future to study these bodies with less atmospheric interference. The Moon, having no air and having permanently dark skies in certain regions, could be an ideal place to install telescopes dedicated to observing comets and interstellar objects. Although it is still a conceptual idea, the passage of 3I Atlas has served as a reminder that these objects do not give much warning and that being prepared would be an advantage. Another aspect that has generated debate is the possibility that these objects transport complex organic compounds or even precursor molecules of life. This does not imply they contain life, but that they could carry chemical ingredients that, under certain conditions, might have contributed to the development of life on young planets. This theory, called panspermia, does not claim that life arrived on Earth in this way, but it considers that the basic elements present in comets and asteroids could have played a role in its development. In this context, 3I Atlas is useful for understanding what type of compounds exist outside our system and how they could travel between stars. All this information contributes to a deeper understanding of the universe. It shows us that the solar system is not isolated, that materials from other systems can reach here, and that science can study them without falling into speculation or exaggeration. As it continues to approach the perihelion, telescopes will keep observing it, measuring its brightness, analyzing its gases, and recording every detail before it disappears. And when it is gone, what will remain will not be fear or danger, but knowledge. As 3I Atlas continues its path towards the perihelion, scientific efforts are intensifying. Ground-based observatories take advantage of every clear night to record data, while space telescopes prepare specific observation windows to analyze it when its brightness reaches the appropriate level. The reason every observation is valuable is simple. Time is limited. After its closest passage to the Sun, the object will move away again into interstellar space and it will no longer be possible to study it with the same level of detail. This makes its visit a unique event within this generation of astronomers. One of the biggest questions has been to know the composition of the nucleus with greater precision. Thanks to spectroscopy techniques, the presence of molecules like carbon monoxide and possibly frozen carbon dioxide has been confirmed, indicating that these compounds begin to sublimate even at great distances from the Sun. The detection of these substances suggests the object formed in an extremely cold region, perhaps in the periphery of its stellar system of origin, in zones comparable to the Oort cloud, but around another star. The ongoing analysis seeks to determine if it also contains complex organic molecules, as has been observed in solar system comets. Scientists have also focused their attention on its light curve. By observing its brightness variations over time, one can infer if 3I Atlas has a defined rotation period, if it has an elongated or irregular shape, or if its surface has more reflective or more active zones. So far, the measurements indicate possible periodic fluctuations, which could suggest the nucleus is spinning, although the data are still being refined. This information is important because it helps to understand how the material is distributed on its surface and how it responds to the sun's heat. The behavior of the expelled gas and dust has also provided significant data. Some observatories have recorded small bursts of activity known as outbursts, which could be due to thermal changes on the surface or the breaking of ice layers that release accumulated gas. Although these outbursts have not been violent or constant, they suffice to indicate the object is not completely inert. Each time one occurs, scientists analyze how the shape of the coma changes and how quickly the released material expands. This allows for the calculation of the gas pressure, the density of the nucleus, and the amount of mass lost to sublimation. Another field of study related to 3I Atlas is its interaction with the solar wind. As it gets closer to the sun, the charged particles emitted by the star impact the gas and dust of the object. This can generate an ion tail that extends in the direction opposite the sun. Although it is not yet clearly observed, astronomers expect this structure to become more visible as activity increases. The shape and orientation of that tail will offer information about the intensity of the solar wind at that time and the density of the interplanetary medium. Orbital analysis continues to confirm that this object follows a hyperbolic trajectory. Its interstellar velocity, which exceeds 25 kilometers per second as it moves away from the solar system, demonstrates that it is not gravitationally bound to the sun. The calculations suggest it travels from a direction opposite the main plane of the solar system, meaning it is not influenced by the usual distribution of planets and asteroids. This unusual inclination also suggests its origin lies outside any known orbit. Astronomers have tried to trace its trajectory into the past to identify which star could have been its place of origin, but so far no precise match has been found. Its journey has been so long that the original positions of the stars have changed significantly due to galactic motion. Meanwhile, organizations continue emphasizing that there is no risk associated with its passage. The object is not expected to fragment dangerously, nor to expel material capable of reaching Earth. Its greatest influence has been intellectual and technological. It has prompted the revision of planetary system formation models, the evaluation of planetary defense strategies, and discussions about the development of missions capable of intercepting interstellar objects. The European Space Agency's Comet Interceptor mission, for example, has gained relevance due to this situation. This spacecraft will be ready to head towards an unstudied comet or an interstellar visitor the moment it is detected. 3I Atlas has also caught the attention of scientists specialized in prebiotic chemistry. These researchers analyze whether the organic molecules present in comets could have been introduced to young planets through impacts, contributing to the formation of compounds essential for life. Although this theory cannot be proven with certainty in this case, studying the organic components of 3I Atlas helps to understand if the chemical ingredients present in our solar system also exist in other places in the universe. What has been observed so far suggests that basic elements like carbon, hydrogen, oxygen, and nitrogen are present in multiple cosmic environments, supporting the idea that fundamental chemical processes could be common throughout the galaxy. Finally, another aspect under discussion is what will happen to this object once it leaves the solar system. When it crosses the heliopause again, which is the boundary where the influence of the solar wind ends and the interstellar medium begins, it will return to an extremely cold and dark environment. Its activity will stop completely and its surface will refreeze. It will continue its journey around the center of the galaxy, possibly without encountering another star for millions of years. On that journey, it will preserve the history of its system of origin and the brief moment it passed near ours. Although its passage may seem silent and imperceptible to most people, for science it represents an unrepeatable opportunity. It is the confirmation that we are not isolated in the universe, that materials from other worlds can reach us, and that with the right technology we can study and understand them. It has not caused destruction, nor mysterious signals, nor changes on Earth. What it has caused is knowledge, cooperation, and a broader view of the place we occupy in the cosmos. The passage of 3I Atlas has highlighted one of the most fascinating aspects of modern astronomy: the human capacity to detect, analyze, and understand objects that come from regions of space completely foreign to our solar environment. This is not achieved with a single tool, but with a precise combination of ground-based observatories, space telescopes, advanced mathematical models, and international cooperation. Every piece of data that arrives about this object goes through scientific analysis networks before being interpreted and published. This rigorous process guarantees that the information shared with the public is based on real evidence and not on assumptions. As the object continues slowly approaching its perihelion, its brightness increases gradually. It is not yet visible to the naked eye, but a faint coma has already been observable with medium-sized telescopes. The coma is a diffuse cloud composed of dust particles and gas sublimated from its icy surface. The detection of this coma confirms that the nucleus is being heated by the sun and is releasing materials that had remained frozen for millions of years. For astronomers, observing the evolution of this coma over time provides clues about the object's internal composition and physical structure. The most recent orbital calculations have also confirmed that 3I Atlas will not pass close to Earth or any other planet in a dangerous way. Its trajectory will bring it closer to the Sun in 2025, and after that it will begin to move away rapidly, losing brightness and decreasing its activity. At that point, it will become increasingly difficult to detect, even with powerful telescopes. This behavior is common in comets that come from cold, dark regions, but in the case of an interstellar object, it has an even more important meaning: there will be no second chance to observe it. In parallel, scientific teams continue observing how it interacts with the solar wind and the sun's magnetic field. Although the activity of 3I Atlas is not as strong as that of some solar system comets, the mere fact that it is beginning to sublimate at such a distance from the sun indicates that its ices are composed of highly volatile substances. This confirms that it formed in an extremely cold environment. As telescopes continue to record data, it is hoped that the presence of ionized gas can be distinguished with greater precision, which would allow for the analysis of how an ion tail forms on an object that had never before been inside a heliosphere. Regarding its nucleus, researchers continue to study variations in the light curve to determine its rotation and shape. The recorded irregularities suggest the object could have a slightly elongated or asymmetric shape, although there is no consensus yet. What is known is that these brightness differences are not pronounced enough to think it is a highly fragmented body or one with chaotic rotation. Its surface seems to be releasing gas relatively uniformly, indicating it does not have large exposed fractures, at least not visible from Earth. On the other hand, theoretical models attempting to trace its interstellar origin continue to evaluate possible stars from which it could have been expelled. For this, astronomers use simulations that calculate the object's movement backward in time, adjusting it to the motion of nearby stars within the galaxy. However, this analysis is extremely complex because stars move over time and small variations in the object's trajectory can completely change the possible point of origin. So far, no star has been found that definitively matches its past trajectory. The presence of 3I Atlas has also strengthened the idea that our solar system is part of a dynamic network of matter traveling between stars. Comets, asteroids, and rocky fragments can be expelled from other systems and eventually cross ours. Some scientists believe this constant exchange of material could explain chemical similarities found in solar system comets with compounds detected in interstellar clouds. This does not mean all these objects share a common origin, but that the chemical processes that occur in nature can be repeated in different places in the universe under suitable conditions. In this context, 3I Atlas becomes a silent messenger from another stellar system. Its passage produces no effects on Earth, but it does provoke an intellectual reaction in those who study the cosmos. Every light spectrum analyzed, every recorded brightness curve, and every refined orbital calculation adds essential pieces to a larger puzzle: understanding how our own system formed and how others form. It is not about finding absolute answers, but about getting closer and closer to a more complete picture of the universe. The most important thing is that all this research is based on verifiable data and not on unfounded hypotheses. There are no artificial signals, no changes in Earth's gravity, no risk of impact. The object is not altering the climate, not causing earthquakes, and not emitting energy outside the natural. What it has actually caused is international collaboration, instrument development, scientific studies, and a new opportunity to observe the universe with more precision. When it finally reaches its perihelion, astronomers will be prepared to record its point of maximum activity. If the object significantly increases its brightness, it could become one of the few interstellar objects visible with small telescopes or binoculars from dark areas of the planet. After that moment, and as it moves away from the Sun, it will stop releasing gas, its coma will gradually disappear, and it will turn back into a dark body traveling alone through interstellar space. And in that silence, all the information it left behind will continue to be studied, because the true value of 3I Atlas is not in its physical presence, but in what it forces us to observe, to measure, to question, and to understand. Its passage reminds us that the universe is not static, that matter travels between stars, and that thanks to scientific knowledge we can detect it, study it, and learn from it without falling into fear or evidence-free assumptions. 3I Atlas continues slowly approaching the nearest point of its trajectory around the Sun, and with each passing day, new data are recorded that allow for a better understanding. Although for most people this object goes unnoticed, for the scientific community it represents one of the most important moments in the study of interstellar bodies. What makes this object so special is not its size or its brightness, but the fact that it comes from another stellar system, and yet, it is now crossing our cosmic neighborhood. It is proof that the universe is in constant exchange of matter and that no solar system is truly isolated from what happens beyond its borders. Science works in silence, gathering information that does not generate immediate visual spectacles but profoundly transforms our understanding of the cosmos. 3I Atlas is not affecting Earth, it is not changing the orbits of the planets, nor is it provoking climatic phenomena. Its influence is intellectual and technological, not physical. It has prompted more observations, generated more precise orbital studies, motivated telescopes like the James Webb to consider specific observation programs, and reinforced the need to have space missions capable of intercepting interstellar objects in the future. As it approaches the perihelion, the amount of gas and dust it releases increases progressively. The coma, although still faint, has been expanding, and some instruments are beginning to detect traces of ionized materials, signaling that the solar wind is interacting directly with the gases expelled by the nucleus. The obtained spectra confirm the presence of volatile compounds like carbon monoxide, carbon dioxide, and possibly small amounts of sublimated water. This confirms that although it behaves differently from common comets, it does contain similar elements, merely preserved under colder conditions for millions of years. Scientists also remain attentive to the brightness variations of the nucleus. These variations allow for deducing whether the object has a slow or fast rotation, as well as its orientation in space. Although no abrupt changes indicating fragmentation have been detected, observations continue to be made to ensure its structure remains stable. Any rupture or drastic change in its activity would be carefully recorded, not because it represents danger, but for what it would reveal about its internal composition and how interstellar materials behave when heated by a star for the first time. At the same time, it has been widely discussed how these objects could be key to understanding the origin of complex organic molecules in the galaxy. Not because they bring life, but because they transport elements like carbon, nitrogen, oxygen, and hydrogen in different chemical combinations. When these compounds form in cold regions of space, they become trapped in the ice and can travel for millions of years until they find environments where they can react. Although in this case there is no possibility of impact with Earth, its study allows for the reinforcement of theories about how the basic ingredients of life could have arrived on young planets over time. The passage of 3I Atlas has also generated discussions about the importance of investing in more advanced astronomical infrastructure. Telescopes like the Vera Rubin Observatory, which will begin operating soon, will be capable of detecting objects like this with much more anticipation, allowing them to be studied from much earlier phases. Furthermore, with the arrival of new space missions, the possibility of maintaining spacecraft in space ready to be sent quickly towards future interstellar visitors is being evaluated. This does not mean they represent danger, but that they are scientific opportunities that only exist for a brief period. When 3I Atlas reaches its perihelion in 2025, astronomers will be prepared to record its moment of maximum activity. That will be the point at which solar radiation exerts the greatest pressure on its surface, possibly causing a significant increase in ice sublimation. It will also be the ideal moment to detect any change in its trajectory caused by the release of gases. After that point, it will begin its path back towards interstellar space, losing brightness and coma until it becomes invisible even to the most powerful telescopes. Although physically it may leave no traces, its passage will have left a legacy of data that will be studied for years. It is possible that in the future what was learned thanks to this object will allow for the detection of more interstellar visitors, the better study of their compositions, or even their interception with space missions. What is being measured, calculated, and recorded today will not be lost, but will serve as a reference for future generations of researchers. 3I Atlas will not transform our world with its presence, but with what it forces us to ask ourselves. It reminds us that the universe is not static, that objects exist wandering between stars, that matter can travel from one stellar system to another, and that with sufficient scientific effort we can discover it, understand it, and learn from it. It is not a symbol of destruction but of knowledge. It does not generate fear but curiosity. It does not change our daily lives, but it does broaden our understanding of where we are within the cosmos. And when it finally disappears into the darkness of space, what will remain is the certainty that, at least for a moment, a fragment from another solar system passed near us and we decided to study it carefully, not out of obligation, but out of the desire to understand the universe in which we exist.